So I'll just start, or I'll just wait for one more minute, or.
Yes, yes. So let me introduce Fan Gao from Hangzhou and his talk on theta representations and their wavefront sets.
Okay, yeah. Okay, thank you. Thanks for Dima for the invitation and for all the audience. Sorry for the delay. Somehow my first time to speak on Zoom. Okay, so I think let me try this. So yeah, okay, good. It works, I think. Okay. Sorry, it's not now. Okay. Hmm? Oops. Uh, so I'll speak on this theta representation. So I have 1 hour, right? Is it true?
Yes.
Wave from.
So, but we have a tradition of asking questions in the middle. So if as a result it goes beyond 1 hour, it's not a problem.
Okay, okay, sure. I'll just try to make it around 1 hour, I guess. Okay, so
yeah, around 1 hour.
Yeah, okay, sure. Okay, so this is based on joint work with I think Wan-Yu Tsai. Okay, so writing on this whiteboard is not extremely smooth, so compared to my OneNote. So, but I will try to balance myself. Okay, so basically, I think my goal is to explain this formula, or rather some speculations on the wavefront sets of theta representations. Okay, so since this is around midnight in Beijing time, so I can afford to make some mistakes if we if we try to call them conjectures. Okay, so so there are 3 parts, I think. So first part is basically a wavefront set, wavefront sets of general pi. Okay, of a representation of, okay, I guess irreducible representation of a general G. Okay, so the second part, I'll talk about I'll basically briefly explain what's theta representation. Okay. And the third part, so that will be the goal, will be just to explain a formula or a conjecture formula for the wavefront set of this theta representation. Okay, of theta. So that will be the goal. So it's quite it's a simple goal, I would say. Okay, so okay, so let me just fix some notation first, some standard notation. Okay, so the first will be I think I will fix F to be a PRD local field of characteristic 0. I assume that this F contains the full group of nth root of unity. So this is the nth root of unity. Okay, so we have that. So okay, so I'll just how am I supposed to start a new page? Maybe just here. Okay, so I will just so this G is used to denote the F rational point. Okay, F point of for me, I will just fix this of a split collected reductive group G over F. Okay, so but for our purpose, we'll also consider some so-called central covering. So meaning we have this I'll just write this G bar, or rather G bar decorated by this parenthesis n to denote some this so we have this G here where we have this subgroup mu n, the full group of nth root of unity inside F. So we are interested in certain central covering of these. Okay, so this is injective and this is surjective, and this mu n, okay, is inside the center of this central extension. Okay, so we're interested in such a central extension, central extension. Okay, so the first part, yeah, is so I'll just discuss about the size of a general pi. Okay, so recall, I think from my undergraduate days, okay, if H is a finite group, and if we have a representation, so if we have a pi, or rather um, pi is a finite representation of this finite group. Is a representation, finite dimensional representation of this finite group, okay, in some representation of this H, okay, and this dimension of this is finite, okay. So of course, a basic information regarding the dimension of V is nothing but you can compute the dimension of this V by just computing the character of this pi. There's a character and then evaluate at 1. Okay, so this is the simplest piece of information we can extract out from this group representation regarding the dimension of V. Okay, so our purpose, our goal is to consider this in general, this so-called irreducible genuine representation of this G bar. Okay, so this G bar is this central covering group there. Okay, so this means just means this irreducible, genuine, irreducible, admissible representation of this central covering. Okay, the only constraint, the only extra constraint we would like to impose here is that this central subgroup mu n acts via embedding. So basically, it means the representation does not factor through a quotient of this G bar. Okay, embedding of mu n into C cross. Okay, so that would be the class of representations we'll be interested in. Okay, so oh, sorry. Yeah. Okay. Okay. So it's a theorem. It's a classical theorem of I think Harris Chandra and Roger Hall. Okay, with some contribution in the covering context by Wan-Yu Tsai, such that we have this basically character expression. Okay, so meaning let me write out more explicitly. So for every pi, this genuine representation. Okay, so we can have we can find open. We have open compact, I guess, subset S pi. This subset depends on your representation, of course, inside the Lie algebra. In this case, the Lie algebra of this G is equal to the Lie algebra of the covering group. Okay, such that of course this subset is around 0. Okay, such that we have the following property that we can do this. We can compute this character expression. Okay, so this is the character distribution of pi. Okay, so we can evaluate, and the test function that will give you this. You can expect along all those nilpotent orbits. So this is the set of nilpotent orbits in this G. Okay, so so the character expression basically says this is a linear combination of some number. Okay, this is a complex number in C. Okay, at times so some measure evaluated at this Fourier transform. Okay, so this guy is probably I should remark a little bit more. So, but before that, let me just complete the sentence first. Okay, so for every test function f compactly supported, and the support is inside this set. Okay. So of course here this I should say this Fourier transform. Oops. This yeah, this depends. Here in particular, it depends on two choices. The first choice is nothing but this carton, this killing form. Maybe we don't have to give it a name, but okay, let me just write out. Okay, the second choice is additive character. Aside from F to C. So it depends on those two choices. And this measure is a certain, I would say, normalized, certain normalized measure on this, on this nilpotent orbit. Okay, so this is a classical theorem.
Excuse me, you don't have to choose a killing form because you can just consider this as a subset of the dual space. You can consider co-adjoint nilpotent orbits, and then you don't have to choose a killing form.
Yes, correct. Yes, I agree. Yes. Okay. Yeah. So okay. So from here we can already just let me give a bit of notation for later purpose. Okay. So for instance, since we are considering this character expression, we'll just write this trace pi to denote those support. Okay. So the nilpotent orbit such that this coefficient is not zero. Okay. So similarly, I will just write this as the maximum. I'll pick out those maximum elements such that the coefficient maximal elements, okay, in this support of the character expression. Okay, so this is inside there. Okay, so this of course this maximal is restricted to the ordering of the nilpotent orbit. Okay, so we also have this wavefront set. I guess different people adopt different terminologies regarding what should be called wavefront set. Okay, but for I think for our purpose, I'll just call the union, the ground union of all those the closure of all those orbits that appears in the character expression. So I will just put this as the wavefront set. Okay, so there are some facts. There are some basic facts. These coefficients. Okay, they are important because they actually encode a large part of the information on the representation pi here. Okay, so the first one, for instance, since we have experts in the audience who know much more than I do, I believe, so I'll just give some general. I will just pick out several representative results. I think so for linear. Instead of diving into all the details, okay. So for linear G, we have actually there exists. So we might be looking at like the lowest coefficient and the highest coefficient, okay. So that's what I'm going to say. So for the lowest coefficient attached to the zero orbit, we know in fact it's more or less just the formal degree. So it's a result of Hertzsprung. There exists this some coefficient depends only on this group, okay, such that this coefficient, the lowest coefficient is nothing but just the formal degree. Okay? Of course, for supercuspidal, I'm restricting myself to supercuspidal representation here. Okay? For all, I guess, unitary supercuspidal representation of this G. Okay, so yeah. Okay, so a remark, I guess, sorry. Okay, so a remark, I guess, is of course we know that this for such supercuspidal, right? We have this. So yes, this C0 depends on C0 depends on pi. Yeah, of course. Yeah. So this guy is related to the gamma factor, or rather the adjoint gamma factor at 0 of this pi. So this is the Hiraga. theta conjecture. So yeah. So the second yeah, okay. So the second thing I want to say, of course, is the highest. Okay. So for this guy in the maximal sets. Okay, so we have at this pi, this it could be covered for covering group. So for covering group, okay, we have this coefficient, okay, with those measures properly normalized, okay. It's actually, of course, the dimension of a certain degenerate with the function. Okay, of course, this is a classical result of Mauchline. Watts per J. I forgot, maybe the 87, 87 or 88. Okay, and for covering group, actually, of course, the idea could be carried through, but the detailed analysis was carried out by Prakash Patel. In I think 5 years ago, part of his thesis. Okay, so of course, the remark is also this. So we know this C, the regular orbit. If you look at the regular orbit, and you ask if it is zero or not, right? So meaning the representation, whether it's generic or not, it's the conjecture of Shahidi that this L parameter is tempered. Okay. So Shahidi. Okay. So I guess what I want to say is, so it seems this I'm not sure, but it seems the question is like, so CO, how this the coefficient for general O, okay, for general O, how is it related to the L parameter? How is it related to the L parameter? I mean, it seems to me it's not, it has not been completely understood. Okay, so like the intermediate nilpotent orbits, except the lowest one and except the highest one. Okay, so I'm not sure how the literature has, how much the literature has covered on this topic. Okay, so my talk today will not be on this, but something relevant, but not directly related to this question. Okay, but to
could you please explain the remark again?
Sorry?
The non-vanishing of what coefficient is equivalent to L parameter being tempered?
The non-vanishing of the attached to this regular.
To the regular nilpotent orbit.
Yeah. Sorry.
But this is equivalent to the representation being generic, right?
Yeah. Yes. Exactly. Yes.
I see.
Okay. So yeah. Okay. So the third thing I want to say is, of course, why this wavefront set is important is, in some sense, it measures how big this representation is. In a sense, for if we have this pi, this representation, let's say for linear group, okay? For covering group, I think probably the proof is, the argument is the same, but to be safe, let me just say for linear group, okay? So one has, of course, this representation, let's say this pi, maybe for pi v, okay? So we have, of course, this representation, you have this decomposition, okay, of this v as those fixed points under the key, right? Key is running over all those basically compact open subgroup. Okay, and the point is, of course, this dimension, the dimension of this is finite. Okay, so of course now it's a reasonable question to ask how the dimension of this v upper k, those vectors fixed by k, how the dimension varies along the volume of k. Okay, so of course the point is this is exactly controlled by the size of the wavefront set. Okay, so we have dimension of v upper k is more or less, is asymptotically proportional to the volume of k and then negative to the power of d. Okay, and this d where this d is nothing but this half of dimension of the wavefront set of pi. Okay, and this is the so-called Gelfand-Kirillov dimension in some sense. Okay, so this explains why we care about this in some sense, because it controls how large this dimension grows since it's very okay. Okay. So, yeah. So in particular, of course, a very trivial example in some sense is for G, right? For G, for instance, if you look at just a character, okay, this is a one-dimensional character of G. Okay, of course the set is just a 0. Okay, and we have the coefficient with those measures properly chosen. Okay, is 1. Okay, so our goal is simple. I would say our goal is very simple. We want to look at the covering analog of such chi. Okay. So yeah. So now let me just explain what do I mean by this covering analog. Okay. So that brings us to the second part. Okay. So this theta representation. Yeah. Okay. So now the data we would like to have in our pocket is nothing but we would like to start with some just one piece of data that will help us to get our covering group. So this is nothing but we start with this y. This is nothing but the co-character lattice of the group G. Okay, so meaning those homomorphism from Gm to T. Okay, so this is a maximal split torus of this G. Okay, so I'm assuming G is a split. Okay? So we will just fix a quadratic form. Okay, so and also we want it to be vowel invariant. Okay, so it is rigidified in the sense that if, for instance, if this group G is simply collected, then this is determined by actually just by one integer. Okay, so yeah. Okay, so we have this now. Okay, so I have to have a new page. So this this theory of Brightness-Gate dealing. Okay. Of course, it has a long history, in particular rooted from the work of Steinberg, but I will just try to be brief here. So that will give us a covering group from this covering group of the G by this mu m. Okay, so the point is to understand this covering group. In some sense, it suffices to understand the torus, the covering torus. Because why? Because this group is this group G is generated by a T and also those unipotent subgroup. Okay, so this is groups. Okay. And essentially because of Hilbert 19, so those unipotent subgroup they split canonically. So we basically have to understand the covering of this torus in order to understand the covering group. Okay, essentially. Okay, so and this covering, of course, by Poolbad, you have this covering torus sitting there. Okay, and now, of course, this projection. Okay, so this is your this Y tensor with F cross. Okay, now this Q, this guy depends on Q because that's what the theory entails. Okay, so the question is essentially how this covering torus is controlled by this Q. Well, it is controlled via the commutator. This oops. Okay. T bar. Okay, since this is a central covering group, so the commutator on this covering torus descend to a map, okay, with two inputs of this linear torus T. Okay, so basically on the generator, you can write out the commutator. which is given by nothing but this is the Hilbert symbol, and some exponent there. This exponent is given in this way. Okay, so this form is nothing but related. This is precisely the part that is controlled by your quadratic form. Okay? Okay. So this is a Hilbert symbol. And symbol. So we have that. Okay. So in particular, one can see. I mean, of course, if n is 1, then there's nothing. Everything is trivial. So this covering torus is a string. Okay, so it's isomorphic as group to mu n cross t. Okay, so what we another guy. There's a whoops, it does not react. Okay, so there's one subtorus. Sorry, there's one sublattice which I call it a YQN, okay, which exactly controls the center. Okay, one can imagine if n is 1, then we expect this sublattice to be equal to y. Okay, so this sublattice, this guy, controls this center. Okay, and one can read off this sublattice from this commutator. So more precisely, you can compute. It is nothing but you are looking at those elements in y such that byz is divisible by n. Okay, for all z. So how this sublattice inside y controls the center? Basically, it is we have this natural map. Okay, we have this natural map from YQN to y, right? This is embedding. So you will induce a map from this YQN cross F, sorry, tensor with F cross. This is some torus there. So you will have a isogeny from this guy to that. Okay, so whatever the image there, I'm going to write it as probably just a T DAG. Okay, there. So this is the image. Okay, you have a natural map there. This is a natural map. This is I, and this is I star. Okay, and this is the image. This is the image of these. Okay, so the current torus is nothing but the pre-image of the center of the current torus is nothing but the pre-image of this group. Okay, so meaning this controls. I think the point I want to highlight is this sublattice controls the center. Okay, so yeah. So now sorry. So let me come back. Oops. So here the point is this is of course this is abelian, no problem. This is abelian, no problem. This is not abelian in general, but this group is not very far from being abelian. Okay, so meaning the representation of this current torus is finite dimensional. The general representation, we have that. We have that in our pocket. One technical thing I would like to say before I give the theta representation is this is so most often we have a very special general representation of the covering torus. We have and we will fix special representation. So let me call it a pi 0 of this covering torus. Okay, so it has the very special property such that its central character is sort of as close to the trivial representation as possible. Okay, it is close to the trivial representation of this center. Okay, by which I mean, well, since this guy, this group is abelian. Okay, so you can imagine, and of course we have this mu n is always sitting inside. Okay, we are looking at general representation, so there's no trivial representation. But we can always ask like how far a general representation of the center here is as close to the trivial one as possible. Meaning, for instance, is it possible it has a character linear? It has a character which lands in just mu n. Okay, so we call such character of this center sort of trivial, and the representation corresponding to this carbon torus is considered as close to the trivial representation. Okay, so yeah. Okay, so what we will have is we consider the genuine principal series. So meaning you consider the exponent. Let me call it lu. Inside this. Okay. So this now this x is the dual of the character lattice. So dual of the co-character lattice. So it's just nothing but the character lattice. Okay. Character lattice law. Okay, so we will have a character, linear character. Okay, if you look at the generator, okay, you will send to just the absolute value of this a, okay, and then exponent. The canonical period of this dual is y. Okay. So y is inside y and a is inside f cross. Okay. So this is a linear character. So we will have from this data, as in the linear case, we'll have this principal series. Okay. So this is nothing but the representation induced from the Borel subgroup, okay, of this representation pi 0 tensor with this character of t. Okay, so this is a representation. This is a general representation of this carbon torus. Okay, general. Okay, so the usual parabolic induction from Borel subgroup will give you this general principal series representation of this G. Okay, yeah, this is what we have. So a very special case. So I think definition. A very special case is if this vector is taking the special form, following Cashter-Patterson, we call it exceptional. If we have the period of this loop with any alpha check is 1, but since we're in the covering settings, we have to normalize this alpha check by putting this normalizing factor n alpha. Okay, so this n alpha is some normalized factor, so it's n divided by GCD of this Q alpha check. And okay, this is a technical part, but it's an important technical part here. Okay, we have to normalize it. So once we have this, for all simple roots, alpha. Okay, so we will have what we will have is this. Okay, we'll have this principal series. Okay, it's a standard module. In fact, it's very reducible and it has a Langlands quotient. Okay, so the Langlands quotient is called the theta representation. Okay, so this is nothing but the Langlands quotient, the Langlands quotient of this representation. Okay, so this is the theta representation. Over there. Okay, so our question, or before that, for instance, one trivial example is I guess if n is 1, okay, so we're in the linear case. Okay, well, if in a linear case, then it's basically this guy. So we can take this pi 0 to be nothing but the trivial character, okay, of the linear torus. Okay, And in this case, this is a character. Is a character of G. I mean, one-dimensional. Okay, the one-dimensional representation of G. Okay. So in the case, for instance, a second example is if n is a 2, but we're specializing to the case where we're looking at the symplectic group. Okay, so we're looking at this guy. Okay, so then we have the theta representation. Okay, so this is the so-called the even wave representation of this. Some people call write it as MP as well, of this metaplectic double cover. Okay, of this guy. So the question we like to ask, okay, it's a naive question, but it has many applications. Basically, is this, okay? How big is the wavefront set? So how big is this? In particular, can you describe the maximum element, okay, of the in the wavefront set of the theta representation? How big is this set? So I think that will be the question we are interested in, and we try to study. Okay, so yeah. So that brings us to the third part. Okay, so it's regarding basically a formula. I mean, it's speculative, so conjecture formula on the maximum elements inside the wavefront set of this. But before that, let me just record some known results. Okay, so I do not have a completely solid grasp on the literature, so let me just state what I know, and my apology for anything missing. They are not intentional. Okay, so let me just have this table here. Okay, so this is my let me just draw some table here. Okay, so maybe this is good enough. Okay, so this is my group G. Okay, this is unfold cover, and so I'd like to look at what is the set of maximum elements. Okay, but since this is sort of concerning the rational nilpotent orbits, so instead of looking at the rational guys, we would like to pass to the algebraic closure. Okay, so we're looking at those stable orbits basically. Okay, so the first family is of course nothing but this I mean double cover. Right? Okay, so for this double cover, we have the I mean this nilpotent orbit is described by partition satisfying certain condition there. Okay, namely the odd numbers will be appearing even times. Okay, so in this case, it is the minimum one. So we have this. Okay, so I'm not sure who first proved this. Okay, so let me not give any attribution. So okay, so the second family. So the second family concerns this SO, this orthogonal group. It's degree 4 cover, but it's sort of double cover. Okay, it's I mean it behaves like a genuine double cover, but okay, so it says the maximum elements inside the wavefront set is nothing but the following orbit, which depends on the parity of R. Okay, so if this R is if R is I guess even, okay, then the orbit is nothing but 2R and then just 1. Okay, and if R is odd, okay, then we have just this nothing but 2R minus 1. Okay, and then 1, 3. Okay, so this I think this is a result of a Baum and Freiberg and Ginsberg probably around 20 years ago. Freiberg. 06. I thought it's 03 or 06. I'm not sure. So let me check later, maybe. Okay. So the point is this is, of course, this is a minimal. I mean, this is a minimal representation. Minimal, meaning the orbit here will be the minimal orbit for this orthogonal group if R is equal to 2 or 3. So a similar example, but not exactly the same, is was considered by ER. So was this G spin. I think 2R plus 1. Okay, so I think double cover. Okay, so it's the same. I would say. Okay, the it's the same. So I can just for completeness, let me just write out. So it's just 2R. Okay, if R is even, if R is odd, okay, so it will be there. Okay, so I forgot which year, probably 17. Correct me, please, if I'm wrong. Okay, so yeah, okay, so yeah, okay, I'm good. Yeah, so yes, it's 17. Okay, so now the other family is this Kirillov covering. Okay, so it's nothing but this A B. Okay, so what is this partition? This partition is nothing but this R. You can divide this R by this N, so you will have this AN plus B. Okay, so this B is lying between 0 and N. Okay, so this is I think it was yeah. So okay, so let me put a question mark here. Okay, so yeah. Okay, so I think this was first worked out by the probably by 7. 7, but unpublished. And then by Yuanqing. Tsai. As part of his thesis, if I understand correctly. Of course, Yuanqing did much more. Okay, but okay, part of it was to show that the orbit was this. Okay, so and later, so okay, so another example concerning this symplectic group is if one consider the the degree 4 cover, actually it was part of Spencer Leslie's thesis that the orbit is this. Okay? It's nothing but this. It was given by the Spencer Leslie. I think probably 18. Okay. Pardon me if I got it wrong. Okay. So I think yeah. Okay. So well, of course the last family. Sorry, I have no room here. Yeah, I don't have. Okay. Maybe I. Okay. Maybe I can start here. So the last family, I would like to say this. Oops, sorry. So the last family, I'd like to say this SP, actually SP2R, N. Okay, but the N is all here. Okay, we restrict to the case of A. So in this case, we have a conjectural answer given by Faber Ginsburg in some recent work. So the answer is nothing but we look at the symplectic collapse of, so the orbit is nothing but exactly the same as the case of general linear group. So it's an A, B, okay? And this R, A and B, they're coming from, you divide R by N, so it's A N plus B, and this B is like that. Okay, okay. So of course, this orbit may not be an orbit for the symplectic group, so we have to take this symplectic collapse. Okay? There. So I was given by the, I think, sorry, if I remember,
can I make a comment?
Yeah, sure, absolutely.
When you started, you talked about the relation of the wavefront set with the L parameter, and you mentioned my conjecture for tempered case. Now there is a conjecture by D. Wajiyang in non-tempered case that what should be the candidate. So I don't know if you're aware of that or not.
I'm not completely aware. I know they have some conjecture for tempered.
No. This is for non-tempered.
For non-temporal, I'm not completely sure.
Well, I mean, DOI is there. He can, I mean, Boeing and I are thinking about these things. So somebody who's, I mean,
Okay,
I think
sure.
it is non-temporal. They just they give a candidate in terms of ortho parameters or what should be the leading wavefront element, the maximal element.
I think yeah, I think now I understand what you mean. Yes, I agree. Yes,
Okay.
I think yeah, John has some conjecture relating other parameter to the
Yeah,
wavefront.
but that would be equivalent to what you were asking. I think that they are not going to be tempered, of course. On the tempered case, you know, there is the conjecture I made, but these are going to be non-tempered. It's a hard conjecture. I mean,
Okay.
Boeing and I think about it all the time. Okay, sorry.
Sure, yeah, okay, yeah, I'll be happy to talk more later. Okay, so of course, I mean, the point of all this, right? I mean, sort of the application. I mean, application of all this is well, so for instance, I mean, two application. I mean, one can do descent, okay, or one can do, for instance, one of the goals I would say is to do this generalized theta lifting. So basically, you like to control the orbit. I mean, you like the theta representation to be sort of small. Okay, if it is not the minimum, and then you expect that the using that as kernel function, you can control the lifting basically. Okay, so so for us, we need we are interested in the general case. So to state this formula, we need three ingredients. So let me just state what are the three ingredients. The three ingredients is basically this. It's nothing but, so we have this. The first ingredient is this McDonald representation of this W. Okay. So what is this guy? So let me briefly explain what is this representation. So it's a irreducible representation of W. So it arises from the following way. So if you have any, in fact, for anything, for any vector, oops, for any vector inside your vector space, okay? So we have this sort of this integral root subgroup, which is given in the following way. It lies in the sort of the root letters. Okay, so this guy, this is a subgroup of the vowel group, and this is generated by generated by those roots, such that the pairing with the root is integral. Okay, generated by this guy. Alpha is a root. Okay, such that this the co-root pairing with so this means the co-root. Okay, pairing with this root is integral. So basically, you are looking at the affine vowel group acting on this vector space, and then you are looking at the stabilizer. Okay, and then you take out the part which lies in the vowel group. Okay, so this is the integral root subgroup here. Okay, so what we will have is we will have this. Oh, I need to start. Whoops, sorry. I have to delete some page. Is that okay? Sorry, this is ridiculous, but
Is this X simply connected root lattice or weight lattice?
sorry?
You have this X simply, I mean, is it W nu minus nu is in X simply connected, right?
This is the root lattice.
I mean,
of course, this is a root lattice.
Character.
No, this is the character lattice, and this is the sub lattice, which is spared by the roots.
Okay, it's a notation. It's a notational problem. Okay,
some people use
just call it, it's just a root lattice. Okay.
Yeah, just root lattice. Yeah. Okay. So So what we have is this. So we will have the sorry. Okay. So yeah. Okay. So what we have is this. We have this so-called J induction. This from this uh, subgroup of the vowel group. Okay. So we will do this J induction of the sign character. Okay. So this is the this is the sign character, okay, of this, of course, okay. So the whole thing, this is a J induction. This is a J induction. I think of those stick spout tungsten. Of course, in the case where we are considering the sign character of this sub-vowel group, it was first considered by McDonald in the in the 70s, I think, maybe 73 or 74, I forgot. Okay, so this is the first ingredient. For instance, of course, two trivial example. There's nothing but if you are doing J induction from W to the self of the character, is nothing but itself. Okay, this is trivial. And on the other hand, if you are doing J induction of the trivial group, okay, of course, in this case, the sign character is nothing but the trivial character as well. Then you will get just nothing but trivial character of the ambient group. Okay, so this is what we have. Okay, so the second ingredient I need is nothing but this Springer correspondence. Yeah, this is Springer correspondence. Okay, so I will not state the full details, but basically, I think if we set this n enhance to be nothing but the pair of Newpolton orbits. Okay, so this is nothing but this O. This O is a stable Newpolton orbit. So meaning you pass to the algebraic closure of this local field, and this eta is nothing but a irreducible representation of the component group of the stabilizer. Okay, so we will get this Springer correspondence, which I get this Springer correspondence. Let me write on a new page. So I'll just write as a SPR. So from the set of irreducible representation of the vowel group to this set, okay, of couples. Okay, so just put this sigma. So in particular, you will get this Newpolton orbit. Okay, I'll write this as the Newpolton obtained is from this correspondence. Okay, so of course this is a stable Newpolton orbit, meaning this guy is actually inside after you pass through the algebraic quotient. Okay, so this is the second ingredient we have. Okay, so the third ingredient is some permutation representation of the vowel group. Okay, so I'll just write as this. Okay, so it's just a representation. It's not irreducible. Okay, it's just a representation. How we get that? So the recipe is nothing but we have this this lattice. Okay. Okay. The vowel group is acting, of course, as reflection on this. Okay, so so this reflection I write as a W parenthesis Y. Okay, so but this gives this representation a twisted way. So we have a twisted action. I put as a square bracket WY by definition to be nothing but Y W and then Y plus rho and then minus rho. Okay, so this is the half sum. I mean, this is the half sum of all positive co-roots. Okay, so once you have these, right? So you will have this permutation of this W on Y. Okay, this is what we get. Okay, but this is not exactly what we want. What we want is nothing but this. What we want is so actually this Y is a lattice, so it's infinite. Okay, in particular, I mean as a set is infinite, but we have this YQN previously introduced probably in the first or second slide. Okay, so this is a sublattice which controls the center, and this is a finite set. Okay, so it turns out this twisted action, this W, this action, okay, on this quotient is in fact well defined. Okay, well defined. Okay, for this guy here, with this y is living here. Okay, this is well defined. So from here we actually get this representation. This is a permutation representation W. It's just a permutation representation on this. Okay. Okay. So this is the representation we have here. So gather this. Now we're going to gather these three ingredients. So we'll have this. I think conjecture with. We're trying to be encouraging ourselves. So let's call it conjecture with Wan-Yu. So it says. It has two parts. So it says for a good covering group, so we call it a persistent. Basically means it's good. Persistent cover, G bar. Okay. Let's say we're in the unramified setting. Okay, unramified data. Okay. What we have is this. We have now we can compute. Okay, conjecturally we can compute the maximum element inside the wavefront set of this theta representation. Okay, of course we can only compute the stable guys after pass to the algebraic closure. It is a singleton. Okay, this singleton, this single stable orbit is nothing but given by we do this. We consider the sign character of this vowel subgroup attached to this exceptional null here. Okay. Now we do this J induction. Oops. We do this J induction from this subgroup, okay, to the whole vowel group. We get a irreducible representation of the vowel group. Okay, now we just apply the Springer correspondence, basically. Okay, so we'll get an orbit. Okay, we'll get an orbit. We'll get a stable orbit. Okay, the formula says it should be that. Okay, so the second part says we have for every orbit inside this set. Okay, we can compute the coefficient in the character expansion, in the Hertzsprung character expansion. So let me complete the sentence. We have this coefficient, of course, with the measures properly normalized, okay, or rather correctly normalized. Okay? So we have this coefficient is nothing but this V representation, this Macdonald representation. Okay, pair with nothing but the permutation representation we obtained just now, but somehow you have to twist by the sign character. Okay? So this is the pairing. This is a pairing. This is a pairing of two representations of W. Okay. So yeah. So this is the. I think this is a conjectural formula we have here. So let me just make a few remarks concerning this. Sorry, I think I'm shooting over time. So so I think probably I can finish within 5 minutes. So I think yeah. So the first remark.
Can I ask a question before you go away? Have you? I mean, there are those examples that you mentioned in. I mean, a bit earlier of the. Have you checked all of these, especially part 2, for those examples?
For part 2, no. That part 2 is the harder part. In fact, I would like to mention something.
Part 1, right? You have checked the first one for all those examples, I suppose.
Not really. I'll mention this probably in 2 minutes. Yeah.
But I mean, should you? I mean, but is there I mean, what is philosophical reason that this should be true? I mean,
well,
I mean, I would assume you would. I mean, the examples would be the only motivation. I don't know. I mean, is this bringing Springer correspondence? Will that be really? How do you know? How do?
Okay, I think okay, probably I would say the motivation, right? The motivation is
Yeah,
coming.
that's what I'd like to know.
Yeah, the motivation is coming from Wan-Yu's work. I mean, okay, basically she did some work in the case of real group. I mean, covering of real group. Of course, in that case, it has to be double cover. But in the case of double cover of real group, this sprinkle correspondence actually appears very naturally there. So now it's very natural to speculate that in the PRD case, this appears as well. Okay. So now, of course, we would like to take this step forward. We like to say this probably is true for PRD case. Of course, as you mentioned, we have to do some sanity check, right? For instance, to say that it agrees with all the existing examples. I mean, like all those things in the previous table I listed. It turns out, yes. I mean, yeah. Okay. So meaning this might give some evidence. I mean, of course, I mean the origin. I mean the motivation was coming from Wan-Yu's work. I have to say that. Yeah.
Okay.
So there are several remarks. I will say okay. So the first remark is this. Probably a zero remark. Sorry. Probably a zero remark is this. So a linear group is always persistent. G is persistent. I mean, linear group is always persistent. So of course, it's a trivial case there. Okay. So the second remark I want to say is this. So or the first remark is this. So so what's hidden here is that of course it says in particular we only have one orbit, right? So this is a singleton. Okay. But of course, I mean, I think this was a long time ago. It was it was conjecture for more general class of representations by Langlands and WIS that this wavefront set, I would say the maximum elements in the wavefront set is a singleton. Okay, so this is like regarding the singleton property and the sorry. So the second thing I want to say is it says for persistent we have this independence. We have this independence on this pi zero. Okay, for this persistent covers. So meaning, although we might have to choose this pi zero, but it does not really matter. Okay, that's what I want to say. Okay, so the third remark I want to say is, well, the natural question probably is, how about those covers which are not persistent? If a cover is not persistent, I would say the first thing is expected to hold as well, but the second will fail. Okay, so that's a case of non-persistent, and we also have a global analog of the first one. Since we can define a Fourier coefficient attached to the important orbit, so in fact, I mean, and as the audience knows very well, we have quite a lot of works on this, in particular from Baum, Friedberg, Ginsberg, and John and his collaborator, including Bain and Savin, and also Gomez and Dima and Sahi, if I pronounce the name correctly. Okay, so that's the global analog, which I didn't mention at all, but we should have that. Okay, so yeah, so that's remark. So I think the only theorem, if I may call it a theorem, is just this. Okay, so let me state this as a theorem and trying to be self-encouraging. Okay, it's nothing but this. So it's nothing but so the first case we would like to say this conjecture holds. Sorry. If this theta is actually generic. Okay. So the second thing is a sanity check. Okay, so basically it says conjecture is compatible with all cases in the table we listed just now. Okay, for instance, cover of SP and cover of GL, cover of orthogonal group and G-spin group. Okay, so in particular, I would say the first family of examples which is still unsolved is the cover of SP, but the degree odd cover. So it belongs to this family and with the let me just say with the conjecture by Freiberg and Gersberg on this SP2R n. Okay, this n is odd. Okay, so this is the maybe I call it theorem we have. Okay, so yeah, so sorry, since I'm shooting over time, so let me just maybe let me just stop here in case that our audience might have some question that might take a longer time. So
yeah. Okay, thank you very much.
I had a question. Maybe you can just go back and one slide. I think I asked if you can elaborate on maybe in the previous slide. Yes, this one. You said that it is independent on pi naught for persistent coverings. Maybe you can mention a bit what these are and is it a conjecture that it's independent on pi naught, or do you know? Why wouldn't it depend?
it's conjectural. It's part of the conjecture. Yes, it's part of the conjecture. It's independent of this pi naught. Of course, this pi naught is not arbitrary. I mean, there are quite some restriction on this pi naught. So most often, not always, most often there's only one pi naught. So so meaning we don't have any choice. So,
yeah.
but for instance, there might be two, like for instance, for degree 4 cover of SL2. So there might be two such pi naught, but it doesn't matter. So that's part of the conjecture as well.
And so the persistent covering in persistent coverings, you can have more than one choice, but it's still independent.
Yes.
And is there some local global property here? Does the cover become persistent, or it's initially encoded in the parameters of the covering?
Oh yeah, that's a good question. Yes, this persistent this property of persistence is a combinatorial property, so it does not concern this underlying field. So it depends only on the quadratic form Q. So it's a local and global property.
Okay. Okay. And now you no longer have any assumption. You no longer have any assumption on like -1 being an nth root.
I guess not. I guess not. I guess not. I would say no. I would say yeah. It does not seem to have this assumption somewhere. Yeah, not that I can say of. Yeah.
So I have a question. Could you give an example of your conjecture, what it tells us about even covers of symplectic groups?
Even cover of the group. Now you mean like
general even covers?
That's a good question. In fact, I could should have sit down and compute that, but I didn't. I mean, like so. I mean, meaning off the top of my head right now, probably I don't know, or rather I don't want to make any wide guess. Like I guess you might be asking like what would be the case like following Leslie, what would be the case of degree 8 cover of SP2R, right? I think
Right.
I think one can compute readily the two sides here. I mean, sorry, I mean the right hand side here. Yeah. I would say, but I didn't compute that, unfortunately. Yeah. I'm sorry for that, but I think I should be able to do that, like, giving me 1 hour, like something like that.
Perfect. No, it's a beautiful conjecture. I'd love to see what it looks like in a new example. My other question is, can you say something about the Archimedean situation?
Oh yeah, yes. In fact, the Archimedean situation was, I think, it's fair to say it was proved by Wan-Yu already. Yeah. Meaning, as part of her thesis, she actually computed this. She actually computed this. I mean, essentially, she computed the leading orbits in the wavefront set. So of course, the methods and the techniques she was using was completely different from ours, I would say, because she was dealing with Harris-Chandra class and utilizing some tools which are only available in the Archimedean setting. So although I think the statement or the formula, one could say maybe one has a Lefschetz principle of borrowing the formula from the Archimedean case and just write it down for the PRD case here. But I would say the proof does not carry over. Yeah,
Great, thank you.
Could you please repeat the last name? Who computed this in the Archimedean case?
Let me put it here. I put it as at the beginning as well. So my collaborator.
Tsai.
Wan-Yu Tsai. I see.
A student of Jeffrey Adams. Now she's in Taiwan. Yeah.
I see.
So Franz, can you explain more on the second part of the conjecture? The right-hand side, does it depend on the orbit O? I think Leslie answered something, but I don't double check.
Sorry, Bayin, can you say that again?
So does the right-hand side of the conjecture 2 depend on the orbit O?
The right-hand side, yes, but not in this direct way. In the sense, by the first part, right? By the first part, this O depends on the right-hand side of the equality from the second part because it depends on this loop. It depends on this loop. So this, because the first part says this O, if you are looking at the maximal guy, right? It depends completely on this loop. This exceptional, this is like the exponent of the Satake parameter. So the O, this O depends on the loop. So
but these are rational orbits.
Sorry?
Do you mean this is the rational orbits or the stable orbits?
No, this is the rational orbit.
Yes, but I mean, is there only one rational orbit?
No, there might be several rational orbits, but the second part of the conjecture says, well, for those rational orbits, the leading coefficient, they are all the same.
Are those same? Okay, I think that's my question.
Yeah,
okay.
but for every, I hope I was trying to be careful enough for every. Yeah.
Okay.
Yeah, but of course, this is only for theta representation. I mean,
okay.
In fact, for persistent cover. I mean.
So you mentioned the global analog. So what do you put it on the first part, the Springer correspondence part for the global? I mean, kind of.
No, I would say the global analog. I will put the first. I mean, of course, the right hand side stays as it is now. Of course, the left hand side is just the maximal orbit of that supports the wavefront. Sorry, that supports the Fourier coefficients. So meaning I would say as I mentioned just now. So the global analog is just as the first equality here. It's just that you replace the left-hand side by the maximal elements that supports the Fourier coefficients.
Okay, thank you.
Are there any further questions? If not, let us thank the speaker again.
Thank you. Thanks for your time.
Thank you very much. So next week we will have a talk by Shamgar Gurevich from Madison. He is not my relative, but he is my friend. And he will talk about a topic that I feel is related. So he will measure representations of finite, of algebraic groups over finite fields. But that's, as far as I understand, that's a joint work with Roger Howe, and this they also define Howe rank for them. And from my experience, I know that for Archimedean fields, Howe rank is related to wavefront sets. So I think it is somewhat related talk. So see you there next week.
Do you have any talks next Wednesday and the Wednesday after? I mean, before the Christmas and the one.
So on December 30, we will not have a talk. Then the first Wednesday of January, so far there is nothing scheduled, but we might have a talk.
But do you have one on the 30th, the one before?
No.
No, okay. And what about on 23rd, the one before Thanksgiving?
Yes, so 23rd is next week. 23rd is Shamgar Gurevich.
But there is nothing after that. Okay, I have to set up something and I don't want it to fall on yours. Okay. All right, so, thank you.
Certainly nothing on December 30 and probably nothing also in the first week of January, but okay, I'm not sure.
Good. I can do some Zoom meeting with some of that. Okay, great. Thanks a lot. Thank you. Was a nice talk, Fan.
Okay, thank you.